Cool, so for question 3, we're going to explain this in two parts. The first part, I will go through a problem-solving process that you might go through when solving this question, and then I'll walk through the solution. Feel free to skip straight to the solution if you prefer. Okay, yeah, so the process to solving this question. So let's just read the question itself first. So yeah, you're given an array of integers of length n. It's strictly it's decreasing until one element, the value, and after that point it's increasing. This essentially just tells you that it's strictly decreasing before and strictly increasing after. Okay, yeah, so when getting a question like this, a very nice thing to do is to start off with an example. And then once you play with an example, it'll give you some intuition about what the question is about. And then you might come up with a brute force solution just to get something to improve upon. Once you get the something to improve upon, you think about how you can do, or how you can make it better. So let's look at an example. And it's randomly picked an example where n is the power of 2. So this thing satisfies the properties specified in the question, which is nice. So now let's think of a brute force solution. Well, one obvious thing that comes to mind is, why don't we just go through all of the indices, 1 all the way to 8, and then for each index checking if a I is smaller than a I plus 1 and a I minus 1. So basically it's like, if this is true, then we're going to return I as the value. So the runtime of this would be O of n, because you have n indices to iterate over, and then each one takes O of 1. Okay, so now we ask ourselves, can we do better than linear time? And if we think about this, like, what's a better runtime than linear? Then it's obviously log. So then we ask the question, what does this mean in terms of like a recursion tree perspective? Well, yeah, basically means that one way to have this is where you have log n levels, where each level does O of 1 work. So something like this, where there are log n nodes, and each node is O of 1 work. And this should remind you of so if we start off with something of size n, then the next one should be like n over 2, next one would be n over 4 until you go to 1. Yeah, so that's an intuition for how the problem should shrink. Yeah, so the idea is that you start off with something of length n, and then you generate a subproblem of length n over 2, and then another subproblem of n over 4, etc. So basically you just keep slicing by half each time. And yeah, so this sounds like a divide and conquer kind of question. So where the recursive call is called on the part that contains the answer, which is like the value. So if we look at our example, so yeah, like it's pretty common to start from the middle as like a marking point that tells us which half to throw away and recurse on. So for this one, the middle element would be 3. And so essentially, you can cut this array in half and then decide which side you can recurse on. So, okay, looking at our example, we can see that the value happens at 2. So this is 1, 2, 3, 6, 7, 8. Okay, well, it happens at index 3 if we're one indexing. And yeah, so this, we're treating this thing as the middle element, and we want to decide whether or not we recurse on this side or this side. So the idea is that when there's only one element left, that element should be the value, which means that every time we do a recursive call, the half that is like thrown away cannot contain the value. So for this particular situation, can the value exist on that side of the array? Okay, no, because the value has to like be smaller than something, and if 4 is greater than 3, the people on the right can't be a value because like 3 is smaller than them, so they can't be a value. So therefore, that means we're going to recurse on this left side. Okay, so we can kind of see a more general pattern or algorithm condition, I guess, which is that if let's say mid element is smaller than right, then it's like recurse on left side, else recurse on the right side. And I suppose it's like recurse and then plus n over 2, because we want to find the index. You want to find j. Yeah, so you just want to find the actual index, not the, you just want to find the index. So you plus add this to kind of balance that out. Yeah, so yeah, anyway, so the idea is that you keep throwing away the part that cannot possibly contain the value. And then so once you just throw away all the parts and you only have one number left, that number has to be the number that's the value. Yeah, so that's the thought process, and then you just formalize this into a solution, 3-part solution. So the algorithm is that, okay, yeah, if you have one element, you just output that element's index, since it's asking for indices. Otherwise, check this condition. If middle is smaller than the thing on the right, that means that means the right half cannot contain the value, and therefore we should recurse on the left half. Otherwise, the right side has to contain the value, and therefore we should recurse on the right side and add n over 2 because we want to find the actual index. When the algorithm is, well, the function, I guess, is called on an array of size 1, then the only possible value is 1, so we just return 1. And now this is kind of reiterating what we had from before. So if the middle number is smaller than the right number, we know that the peak can't be on the side or the half of the array that's on the to the right of the middle number, and therefore we're going to recurse on the left side. Yeah, and by induction we're going to assume that the function does what we want it to do, i.e. find the value in that array. And then similarly, if the middle element is greater than the element directly to its right, that means the value in this big array has to be on the right side. Therefore, we're going to recursively call on the right side, and by induction, we're going to assume that the function does what we wrote it to do, and therefore it will find the smallest, or it will find the value on the right side, right half of this original array, and therefore this function will return the index of the value. And we add n over 2, because if it's not in the first half, the left half, that means its index would be n over 2 plus whatever is returned from the right. Okay, runtime. Well, the subproblem gets halved every single recursive call, and each recursive call only does an if check, which is O1, so then it's O1 times log n, so therefore it's O of log n.